Welcome back to the classroom. My name is Mr. Wong. Today we'll be going through Module 5 of Inquiry Question 3, which is the motions in gravitational fields, and we are going to be looking at this particular dot point here. So our title for this lesson is on Kepler's laws of planetary motion. We're going to actually investigate what that actually means and how it relates to Newton's formula of gravity. And we're going to try and derive a relationship between gravitational force and an object's planetary motion. Textbook reference, here you go. Right, so I want to go and talk about this person called Johannes Kepler. He published a book, and he also talked about space and how objects orbit around other objects in space here. This is obviously after Galileo's time. I think around about the same time as Newton or just before. So he came before Isaac Newton, and he actually provided some really important observations about the way objects rotated. So he was a believer of the heliocentric model, where the sun was at the center of the universe and everything orbits around it. And he came up with 3 particular laws to explain the kind of motions we see and everything about. Now, these particular laws, whilst he did create it for planets orbiting around the sun, you can apply it to any type of satellite orbiting around any large mass object in space. So, law 1, orbits are in ellipses. We'll go through each one. Law 2, the distance or the area covered from a traveling star is the same for a given period of time, even if different orbits include elliptical orbits. And law number 3 is that the period square of a planet orbiting around the sun is equal or proportional to the length of the distance from the major axis cube. That all sounds a little bit confusing, so we'll go into a bit more detailed explanation. So Kepler's first law of planetary motion basically states that all planets move in elliptical orbits with the sun at one focus. What we mean by a focus here is originally when people assumed how planets orbit around the sun, they assumed it was perfectly circular. However, what we notice is the planets actually don't do that. So say the sun is in this position here, you can see the planet as it orbits around. At this point here, it's closer to the sun. And then if it was at this point here, it's further away from the sun. So it creates that sort of egg shape or elliptical shape of the orbit. Equivalently, we could just say each planet travels in an elliptical orbit around the sun, and that's our focal point there. There are 2 focal points that can be used to help determine the shape of the eclipse, but we won't get into big detail on that. But what you can probably understand is when the planet is in this particular direction, it's moving very fast. And the reason why it moves very fast goes back to our equation for gravitational acceleration. As you can see here in this length, r is small. And so there's a greater gravitational acceleration dragging our planet in here. And then it begins to accelerate away and off over here where the radius distance is quite large. So the period takes longer. So that's what you see with the 2 motions here. Here we have it really fast because the gravitational acceleration is quite large here. And then so we get this acceleration along this position here. And then as we go over here, begins to slow down because that's the furthest point, and so gravitational acceleration is at its weakest point in this eclipse. So the planet will look like it speeds up and then it slows down as it goes around. The second law actually states equal areas covered in equal amounts of time. So we talked about how the planet, when it's closer towards the sun, will be accelerated, and so it moves a lot faster. And how when it's further away, it moves a lot slower. However, if they cover the same amount of time, so say this was 20 seconds, and this was 20 seconds, if we actually try and calculate the area in which they covered from that starting point to the end point, it would be the same area. Okay, so there's that. That's what the second law basically states for us. Okay, and as we talked about here, as the planet approaches the sun, gravitational force increases. Technically, gravitational acceleration increases, and that leads to a greater orbital speed. And here we get a lower orbital speed because there is a decrease in gravitational acceleration. Okay, now moving to the third law. So from his calculations, he actually found a really interesting relationship. He found that the square of the period of a planet's orbit is directly proportional to the cube of the mean radius of its orbit. What that essentially means is the period in which it takes a planet to orbit around the sun was directly proportional to the average radius that it was away from the sun. Obviously, we have this period square and a radius cube. I just didn't mention it just to make it a little bit simpler, but that's the relationship we have here. So each planet here, if you actually look at this, we have the square orbital period down here, and we have the cube of the radius here. You can see each one of these planets fall under this line of best fit of ours. So the ratio between the two is constant, which means if I know how long it takes for the Earth to orbit around the sun, and I know the average radius it makes, I could actually use this value to help me work out, how long does it take for Jupiter to do the same, to do that orbit, or one orbit, or, how far is it away from the sun on average, if I know how long it takes to orbit around that sun. Because, these are constants. They are both the ratios that they create, t squared over r cubed or r cubed over t squared, will be the same as each other. So we can also rewrite the equation like this. A nice little ratio to depict how using potentially the orbital radius and orbital period of one planet can help us find the orbital period or radius of another planet. Okay, so if two objects orbit the sun, we can work out the following relationship. Like we said, r is the length of the semi-major axes, so just the center point of the mean average that the orbit is occurring at. So that's what we mean by that. Don't get too complicated over this particular diagram. Obviously, the planet doesn't always have the same radius, but we're just going to use an average, and it seems to work really well with Kepler's law. This is his third law as well. So let's just quickly summarize his three laws. First law is that all planets move in an elliptical orbit around the sun at one focal. So focal as in the position of where the sun is. We also know that the lines connecting a planet to the sun sweeps out the same amount of area in the same interval, even though if the planet is closer towards the sun, it's traveling faster, and if it's away from the sun, it's traveling slower. And then number 3, for every planet, the ratio of the cube of the average orbital radius, r, to the square of the period revolution time is proportional to each other, and it gives us a nice constant, and it allows us to work out the orbital radius or average orbital radius and revolution time of other planets orbiting the same mass object. Okay, so as you can see here, different planets, this is just an illustration of Kepler's law. You can see that the further we are away from the central mass, it's much slower. As it gets closer, it gets faster. We can also see, or you can't really see this one, but the time it takes will be, or the time it takes to move from one position to another will cover the same area, obviously assuming for the same planet that's orbiting. However, using Newton's third law, which I'll write it out again, if I know the ratio, let's just call it a constant, if I know how long it takes for this orbit here to do all its rotation, and I know, what the distance is for different planets, I can actually find how long it takes for it to orbit around like so. So it's a really handy mathematical law that he developed. But there was an issue. So one of the problems with Kepler's original equation here is it measures everything in astronomical units. So it doesn't really take into account, SI units and forces. So what we're going to do now is show you how the fusion of Kepler's planetary motion and Newton's universal gravitational law actually come together. Okay, so if we look at a satellite, the origin of its centripetal force comes from its gravitational force. Okay, so we can express the mathematical relationship like so. Okay, our net force, the centripetal force, is caused by the gravitational force of a larger object onto a smaller object. If we look at this formula here, this is the formula for centripetal force, and this is the force of universal gravitation. Now, if we look at the smaller object, we already demonstrated that it is quite, if we actually look at this, the smaller object, its masses will cancel each other out on both sides of the equation. The radius will cancel. We're left with just one r here. And we find this lovely little equation at the end. V squared equals to big G over times big M over R. And then we get, if we root the square here, we get this here. Now this is the orbital velocity, as in the speed, the tangential speed the satellite would have as it's performing uniform circular motion around a central mass. Okay. Now we can also do a little bit more. We can actually demonstrate going back to this exact same formula or this same component formula here. We can actually then implement Kepler's third law. All we know is V equals to 2 pi r over t. So in this bit here, instead of moving the square over, we substitute for 2 pi r over t squared. And if we write our equation out, we get this formula here. Now, if you actually have a look, we already have t squared. So now we just need to rearrange to get r cubed over here. And we can move the 4 pi squared down here. And there you go. This encompasses the formula, or this encompasses Kepler's law on this side here. And it takes into account Newton's law of universal gravitation. So we can actually demonstrate how much time it takes for an object to rotate around a larger orbit around a larger object based on these components here. What you can notice is the mass of the smaller object does not play into how long it takes for it to orbit around the larger object. So our planet, Earth in this case, it doesn't matter how big or small it is, its own mass won't influence how long it takes to orbit around our sun. And this is what the formula is showing here with Kepler's law. You can also prove that using orbital velocity here as well. This is not given to you in your syllabus or in your data sheet, so you do need to remember this one. Okay, so these are all the formulas we can come up with here to demonstrate all the different relationships. Okay, so what we'll do is just quickly go into some calculation questions and then we'll go on from there. So question 1, it says calculate the periods of 2 different satellites orbiting the Earth at these separate latitudes or altitudes, and also the orbital constants for Mars, in which case here and here. Right, so in this one, since I'm low on space, I'll show you the answers in about 5 seconds. What you can do is just pause the video here. All right, let's show you the answers. So for question 1, the period of the 2 satellites can be presented here. So it'll take about 5,380 seconds, and B, it'll take about 99,500 seconds. In question 2, we have the planet Mars. So here are the values here for our answers. Values for our answers here, and value for our answers here. I might do a separate video later on to go through these calculations, but I'll just show you these calculations here. And last we have is question 3 and 4. Pause the video here if you would like to try. I'll show you the question. I'll show you the responses here. Okay, so those are our things here. All right, so that concludes our discussion about Kepler's 3 laws of motion and looking at how we can derive his 3rd law and incorporate it into Newton's universal gravitation. Okay, so I'll leave the video here. We'll go back into those calculation questions very shortly, so stay tuned for that. Thank you for joining. I'll see you next time.